Welcome to Sri Jayendra Axon. Good morning, all of you. Today we are going to discuss chemistry, chemical bonding, and molecular structure. So, what is chemical bonding and molecular structure? We are going to discuss today in this class. Very important chapter for all competitive exams. Yes. Coming to chemical bonding and molecular structure. So, in this chapter, we are going to learn about different types of bonds, with what force the atoms will attract with each other. That only we are going to discuss. So, here, introduction, coming to introduction. A chemical bond is defined as a force of attraction which holds the atom together in a molecule. The first approach to the atoms in a molecule, the first approach to the atoms in a molecule to explain the chemical bond formation is given by Cosil and Lewis. So the first approach was given by Cosil and Lewis. So what is a chemical bond? It's just basically a force of attraction with which the atoms hold together in a molecule. So a chemical bond is defined as the force of attraction which holds the atoms together in a molecule. So there are so many types of bonds which we are going to discuss in this chapter, and this chapter is very important for all competitive exams. So listen carefully. What is a chemical bond? Just a chemical bond is nothing but the force of attraction which holds the atoms together in a molecule. I hope it is clear. So the first approach explains the approach to explain the chemical bond formation is given by Cosil and Lewis structures. So Cosil and Lewis are the scientists which have given the approach to the chemical bond formation. So according to Cochen-Lewis theory, the atom is considered to be a positively charged kernel. Here you see that it is a positively charged kernel. Kernel means just like house. You can say dog kernel will say that is nothing but house. House. So a positively charged kernel and the outer shell can accommodate a maximum of 8 electrons. 8 electrons based on octet rule. So he assumed that these 8 electrons will occupy the corners of a cube. For example, in sodium atom, only one corner is occupied by the outermost electron, while in a noble gas, all 8 corners. Why it is happening here? In sodium atom, only one corner is occupied by the outermost electron because sodium has atomic number 11. So its configuration is 1s2, 2s2, 3, 2p6, 3s1. So it has only one electron in the outermost shell. So it is occupied by outermost electron, only one corner. While in noble gas, as you know, except helium, all other noble gases have 8 electrons in the outermost shell. So, while in a noble gas, all 8 corners are occupied by the electrons. This octet state of atom is most stable electronic arrangement. So, already we know how can we say an atom is stable. If it contains 8 electrons in the outermost shell, we can say it is 100% stable, and that type of atoms will not take part in the chemical reaction. And all other atoms will try to get stability by taking part in the chemical reaction or by the bond formation. So in this chapter, we are going to discuss about chemical bonding only, that is bond formation between the atoms in a molecule. So next we have, what is the Coser-Lewis approach? According to Lewis, According to Lewis, the atoms will enter into chemical bond formation in order to attain this stable octet arrangement, as I told you before. So, why do atoms combine? They are combined with each other. They combine with the same atoms or they combine with other atoms only to attain this stable octet arrangement of electrons in the outermost shell, which is very important. Example, you see, in case of sodium and chlorine, both atoms can attain the octet arrangement by transferring the outermost electron of the sodium to outermost shell of chlorine. Why it is happening? Because sodium has sodium has one electron in the valence shell. So for example, if you take sodium, so sodium, if you take into consideration, here I'm writing here, sodium, its configuration is 1s2, 2s2, 2p6 and 3s1. So this one electron has, if it loses this electron, if it loses this one electron, we can say it is stable because it has 8 electrons in the outer motion, that is 2s to 2p6. So for doing this, what happens? As it has one free electron, we cannot say it is extra electron, we'll say it is one free electron. This sodium, as it has one free electron, sodium loses that free electron. and becomes the substance which loses electron will get positive charge. So she has Na plus. And chlorine, if you see chlorine atomic number, it is 17 already, you know. Since chlorine atomic number is 17, it requires one more electron for adding stability. That electron it will get from sodium, and sodium will transfer its electron to chlorine. As chlorine is gaining the electron, it will get negative charge. Formed are more stable than sodium or chlorine atoms. So in case of Cl2 also, Cl here what happens? Cl2. One chlorine will contribute, yeah, will combine with another chlorine to form chlorine molecule, hydrogen molecule, fluorine molecule, oxygen molecule. These are all diatomic molecules, etc. The atoms will attain the octet arrangement only by sharing of electrons between them. So only we have two types of, mainly we have two types of bonds. One is by transferring the outermost electron of the atom to another atom, whereas another case it is by sharing of electrons between them. So these two are very important. So here the atoms will attain stable configuration either by stable octet arrangement, either by donating electron or by accepting electron or by sharing electrons. So in this is the Lewis approach now. So that is Coastal-Lewis approach. Now we can see lower this Lewis approach. The Lewis symbol of an atom will have the representation of outer shell's electron only. The inner shell's electrons which do not participate in bond formation are not represented in Lewis dot symbols, that is Lewis structures. So only according to Lewis symbols, we will discuss only about the outer shell electrons only, outermost electrons only. So the Lewis symbol of the second period elements are given below. For example, what are the second period elements we have? So we have lithium, beryllium, boron, etc. So lithium will have only one electron in the outermost shell. Beryllium will have two electrons. Carbon will have four electrons. Nitrogen will have five electrons. So outermost electrons only we'll discuss. And the Lewis symbols are nothing but they represented only the electrons, atoms in the outermost electrons only. Like fluorine will have seven electrons and eight electrons for neon. So the Lewis symbol of an atom will have the representation of outer shell electrons only. The inner shell electrons which do not participate in the bond formation are not represented in Lewis symbol. So I hope it is clear. Next. So the number of dots around the symbol of an atom represents the number of valence electrons present in the atom. So each dot is one electron. So the valency of the atom is equal to the number of dots around the symbol, 8 minus the number of dots in the Lewis symbol. In case of non-metals, we'll take, if it is more than 4, we'll take 8 minus 4. If it is 5, 8 minus 5. If it is 6, 8 minus 6, like that. So 8 minus the number of dots in the Lewis symbol. So that is called the valency. This valency topic we have discussed already in periodic table. So the Lewis dot structures of the molecules indicate the type of bond formed between the two atoms. So this is nothing but significance of Lewis symbols. So each dot represents one electron. That is most important. And the number of electrons is nothing but valency. If it is more than four electrons, like for example, in the case of nitrogen, if you see, nitrogen has five electrons in the valence shell. So nitrogen valence is taken as 8 minus 5. 8 minus the number of dots. So that is 5 dots. I hope it is clear. Next. Octet rule. According to octet rule, atoms can combine with each other either by transfer of valence electrons from one atom to another atom or by sharing valence electrons in order to attain the stable octet configuration. So by this what we can understand, only the valence electron will be involved in the bonding, not the inner electrons or the core electrons. Only valence electrons involved in the bonding. So according to octet rule, atoms can combine with each other either by transfer of valence electrons. So here I'm underlining two important lines. So these two lines you have to note down in your classwork. So that done can be by transfer of valence electrons from one atom to another or by sharing of valence electrons in order to attain the stable octet configuration. And once the atoms gets octet configuration, they are stable. So I hope it is clear. So this is very, very important. So atom will either, according to octet rule, the atoms can combine with each other either by transfer of electrons, valence electrons, from one atom to another, or by sharing of valence electrons. Here, the valence electrons are important. So this is clear now. So this is called octet rule. Next, types of chemical bonds. So we have totally four types of chemical bonds mainly: ionic bond or electrovalent bond, covalent bond, coordinate covalent bond, and finally hydrogen bonding. So in this chapter, we'll discuss about these four bonds. After this, we have molecular structures of, that is nothing but chemical bonding and molecular structures. So first we have total how many types of bonds? Four bonds. What are those? Ionic bond or electrovalent bond, covalent bond, coordinate covalent bond, and hydrogen bond. In school level, we learn what is ionic bond example only. But here in, as we are going to do it with objective questions, so we have different types of different matter we have. Means the extended part of ionic bond and electrovalent bond we will be learning in this class. Next, covalent bond along with coordinate covalent bond and hydrogen bond. And I think hydrogen bonding is not there in school level. Only ionic bond, covalent bond, coordinate covalent bond we'll be having. So first we'll discuss what is ionic bond or electrovalent bond. So the electrostatic force of attraction, very important here. Electrostatic force of attraction. What is electrostatic force of attraction? So the substance will, one atom will lose electron, another atom will gain electron. So which holds two opposite ions, two opposite ions. This is I. Here it is nothing but I. So two opposite ions together is called as ionic bond. Here also you can see it has come nothing but I. So it is nothing but ionic bond. So ionic bond. What is ionic bond? Electrostatic force of attraction which holds oppositely charged ions, which hold two oppositely ions together. Oppositely charged ions we can write here. We can write here charged ions. So charged ions. So that is nothing but called ionic bond. Example, if you see here, I'll just write the formation of ionic bond. Sodium atom. So for example, sodium, the configuration of sodium is 1s2, 2s2, 2p6, 3s1. And chlorine is 1s2, 2s2, 2p6, 3s2, 3p6, 3p5, sorry, 3p5, because the atomic number is 17. So for attaining noble gas configuration, it requires one electron. One electron is required, and here it is having one electron extra. So one electron, one free electron we write here. We cannot write extra. So one free electron. So sodium loses its electron. Sodium, here I'm writing here clearly. Sodium loses one electron and forms sodium ion, whereas chlorine gains that electron. Just I'm writing only example point of view. Exact figure you will have differently that we will discuss in Born-Haber cycle. So sodium loses one electron and forms sodium ion. So these opposite charged ions will come closer to form NaCl crystal, that is sodium chloride molecule. So electrostatic force of attraction, because one is having positive charge and there is having negative charge. So which holds together opposite charged ions together is called as ionic bond. So I hope it is clear. So next we'll continue with, it is formed due to transfer of electrons from one metal to a non-metal. So here important is, already I told you. So it is always formed between metal and non-metal. So here metal to non-metal is important. Always ionic bond is formed between ionic bond or electrovalent bond is formed due to transfer of electrons. Transfer of electrons, that is also valence electrons only. So here we can write transfer of valence electrons from metal to non-metal. So this is very important. So this is called ionic bond. Next, the number of electrons transferred during ionic bond formation is known as electrovalency of the atom. The number of electrons transferred during ionic bond formation is known as electrovalency of an atom. So how many number of electrons transferred during ionic bond is called electrovalency. For example, as sodium is donating only, as sodium is giving out only one electron, so its valency is nothing but one. If magnesium, if we take into consideration, its valence is two. Aluminium, if we take into consideration, its valence is three, and so on. So the number of electrons transferred during ionic bond formation is known as electrovalency of the atom. In sodium chloride, the outermost electron of sodium is transferred to the outermost shell of chlorine. Thus, the electrovalency of sodium is plus one, and that of chlorine is minus one because it is accepting one electron. So I hope it's clear. So what is electrovalency? Electrovalency is nothing but number of electrons transferred or number of electrons gained. I hope it is clear now. So it's very simple, but here it is up to school level. We'll discuss this only. But now here we'll see more about this ionic bond in the next session, in the same session. So factors favoring formation of ionic bond. Very, very important. The ionic bond formation depends on two factors. First one you can see here is a formation of positive ions. Means what? How much easily it can lose that electron. Anyway, metal will have either one electron or two electron two free electrons, two valence electrons. So that how much easily it can formation of these positive ions means not how much easily it can lose that electron, that is called ease of formation, and how much easily it can gain the electron, that is called ease of formation of negative ions. So based on these two factors only ionic bond mainly depends. So the formation of positive ion involves the ionization of an atom. The formation of positive ion involves the ionization of an atom. If the ionization energy of an atom is less, it forms positive ion. The ionization energy means the energy required to remove the outermost electron, outermost electron of a neutral gaseous atom. Gaseous atom is also important. Why it is gaseous, we'll discuss later. So it forms only positive ion more easily. The formation of negative ion involves addition of electron to a neutral atom. So how much easily it can gain that electron because of its electronegativity. If the electron gain enthalpy of an atom is more, so here the important point is electron gain negative. Electron gain enthalpy of atom is more negative. It can accept the electron more easily and get converted into negative ion. So the main factor is first lower ionization energy for metal. So low ionization energy for metal and high electron gain enthalpy for non-metal. If these two combinations are there, then it is a perfect ionic bond. If these two combinations are there, then it is a perfect ionic bond. So I hope it is clear. So the main two factors is ease of formation of positive ions and ease of formation of negative ions. So ease of formation of positive ions and ease of formation of negative ions. These two are most important. I hope it is clear. So the factors favoring ionic bond formation is ease of formation of positive ion means it should have low ionization energy. Low ionization energy. So again, writing here, if you want, you can write in your classworks. It is nothing but low ionization energy, and here nothing but high high electron gain enthalpy. High electron gain enthalpy. So I hope it is clear now. So these are the main two factors which is affecting ionic bond. So here I'm doing it now. So there is nothing but these are the two factors. I hope it is clear. So next, factors favoring ionic bond. Thus, the ionic bond formation is favored by low ionization enthalpy of the cation forming atom and high negative electron gain enthalpy of anion forming element. So thus the ionic compounds have cations which are metallic elements and the anions which are non-metallic elements. Only exception is ammonium ion NH4 plus which has two non-metallic elements and forms many ionic compounds. So here this is an exception. So all the exceptions in this case is very important. So in inorganic chemistry, if you are seeing about more exceptions, so here exception is ammonium ion. Beside even it contains nitrogen and hydrogen, both are nonmetals, but still it has forming many ionic compounds. So ammonium compounds are ionic in nature. So this is an exception point. Some more exceptions also we can see here. We can do it. I hope it is clear now. So next. So what do you understand by this? The ionic bond formation. The ionic bond formation is favored by low ionization enthalpy of the cation and high electron gain enthalpy of anion forming element. So they should have both of them should have, one is should have low ionization enthalpy, that is cation, and another should have high electron gain enthalpy, that is anion. I hope it is clear. Next. So if the electronegativity difference between two atoms is greater than 1.7, means one should be highly electronegative, one should be low, very low electronegative. So if your electronegative difference between metal and non-metal is greater than 1.7 or 1.9, ionic bond is favorable. As per Fuzzen's rules, factors favorable for the ionic bond formation is very, very important Fuzzen's rules here. So Fuzzen's rules you can concentrate. So as per Fuzzen's rules, factors favorable for ionic bond formation is first one we have large cation. Large cation in the sense the atomic number should be very high, and small anion, the atomic number of non-metal should be very low. Low charge on cation and anion. So for example, if I say here large cation, for example, if I say large cation means here, I'll show you what is large cation. If we take cesium, cesium plus, it is having atomic number more down the first group, last element, except apart from francium, it is cesium is a last element, cesium plus. And if we take the anion F minus, and in the case of suppose you take sodium plus, which is top in the pair, that is first group element, and F minus. In these two, which is most ionic? Cesium fluoride is most ionic than sodium fluoride. Why? Because large cation, small anion favors ionic bond formation. So this is more ionic than sodium fluoride. I hope it is clear. In the same way, low charge on cation and anion. Low charge on cation means only one. For example, if you take magnesium plus 2, Mg plus 2. And so, for example, if you take Cl minus 2. So Cl anyway it forms one Cl only. So if you take Mg plus 2 and if you take one more radical that is sulfate, SO4 2 minus. Even though magnesium sulfate is ionic nature, but sodium fluoride is more ionic than magnesium sulfate because low charge on cation and anion is favoring ionic bond formation. So with these two examples it is clear. So first as per Fuzzen's rules, what are the favorable conditions for ionic bond? First condition is First condition is large cation, small anion. Second condition is low charge on cation and anion. So if it is low charge means plus one. If it is a plus one, we'll write only plus. Plus two means we'll write plus two. Plus three means plus three. So minus three, minus two, minus one. So magnesium oxide, if you take O minus two and Mg plus two. So this is less ionic than sodium oxide, Na2O, because small charge on cation, large charge on anion. So low charge on cation and low charge on anion, low charge on cation as well as low charge on anion will favor ionic bond formation. And one more difference, if the electronegativity difference between two atoms is greater than 1.7 or 1.9, ionic bond is favorable. So these 2 points, this slide is very, very important for competitive exams because they'll ask in the competition exams which are the following is most ionic, or which are the following is most ionic. That is one type of question. And they'll ask one more question. The electronegativity of A is this much value and the electronegativity of B is this much value. The bond formed between AB is, if the electronegativity difference is greater than 1.7, what is our assumption? If the electronegativity difference between A and B is greater than 1.7 or 1.9, ionic bond is favorable. Suppose if I say electronegativity of A, they'll give some value, and electronegativity of B, they'll give some value. And they ask us the bond formed between A and B is ionic or covalent. Just you have to do difference. Difference means electronegativity of A minus electronegativity of B. If you do, then if it is greater than 1.7 or 1.9, the ionic bond is favorable. Otherwise, it is a covalent bond. It is covalent bond. I hope it is clear now. Next. So these are the favorable conditions for ionic bond. Next, we have structure of ionic compounds. So what are the favorable conditions of ionic bonds we have already discussed. Now we will discuss what are the structures of ionic compounds. Ionic compounds exist as crystalline solids which has definite orderly arrangement of cation and anions in three-dimensional lattice, that is space. So ionic compounds exist as crystalline solids. Usually almost all the ionic compounds are crystalline solids. Very, very important. That's why their boiling point is very high. So almost all the ionic compounds are crystalline solids. That's why their melting points as well as the boiling points are high, which has definitely orderly arrangement. So these solids will have definite orderly arrangement of cations and anions in three-dimensional space lattice. That is, three-dimension means, you know, the three-dimension like cuboid. So these ions are held together in the crystal lattice by strong electrostatic force of attraction. So with what force they attract with each other? Strong electrostatic force of attraction. So out of all the bonds, ionic bond compounds are the having strongest attraction between the two combining species, that is ions. So that is nothing but what force? That is called electrostatic force of attraction. So different ionic compounds crystallize in different crystal structures. The crystal structure depends on size of cations. So the crystal structure depends upon size of cations and anions of the ionic compound. So these points are very important. So these are nothing but the crystal structure depends on the size of cations as well as the anions of the ionic compound. So this is nothing but the structure of ionic compounds, and more about structure of ionic compounds you will be learning in class 12. That is the chapter name is solid state. So structure of ionic compound, example, sodium chloride has the following structure, which is known as rock salt type structure. That's why we'll call sodium chloride is rock salt. So rock salt structure, you can have this 3D dimension. Here chlorine ions and here sodium ions. Small rounds, small spheres represent sodium ions and big spheres represent chlorine ions. So they arranged in the cube, that is 3D structure like this. I hope it is clear now. So next we have lattice enthalpy and lattice energy. In ionic solids, the sum of ionization energy of the cation forming atom and electron gain enthalpy of anion. Already we know. So we'll take the ionization energy of cation and electron gain enthalpy of anion. So if you add these two, that is sum of ionization energy of the cation forming atom and electron gain enthalpy of anion forming atom is still positive, at the formation of ionic compound takes place. This is due to the energy released when cations and anions get attracted towards each other to form crystal lattice. This energy is known as lattice enthalpy or lattice energy. In simple words, if you say the energy released or liberated during the formation of ionic compound is nothing but lattice energy or lattice enthalpy. Very, very important. The energy released during the formation of ionic compound by two species, that is cations and anions, is nothing but lattice energy or lattice enthalpy. So with what force they bind together, that much force is being released, because based on law of conservation of energy, energy is neither transferred nor created. Only neither energy is neither created nor destroyed. Only it transfers from one form to another form. So whatever the energy of cation, whatever the energy, with what energy they attract with each other, the same energy they should release, and that releasing of that energy is nothing but lattice energy or lattice enthalpy. Coming to first compound, so if the sum of ionization energy of the cation atom and the electron gain enthalpy of anion forming atom is still positive, the formation of ionic compound takes place. This is nothing but lattice enthalpy. So I hope it is clear. So what is lattice enthalpy? We'll be knowing more now. So lattice energy or the lattice enthalpy is defined as amount of energy released. Here important point is amount of energy released, because it is only exothermic process, is not endothermic process. So all lattice enthalpy is exothermic process. The amount of energy release, here the amount of energy release is very, very important. When 1 mole of an ionic compound is formed from its constant gaseous ions, very important is gaseous ions. The energy amount of energy required to break 1 mole of solid ionic compound into gaseous constant ions. Either the reverse energy is also energy required to break 1 mole of solid ionic compound into its gaseous constants, gaseous constant ions, that is Na plus and Cl minus gaseous form. So that is nothing but lattice enthalpy or lattice energy. So I hope it is clear now. Next we have, so amount of energy released when 1 mole of the ionic compound is formed from its constant gaseous ions. This is called lattice enthalpy. Next, so for example, Na plus Cl minus. Here gaseous Na plus ion and Cl minus gaseous is forming for finally solid sodium chloride. So delta H is called lattice enthalpy, and it is observed as minus 788. Means this much of energy is released during the formation of sodium chloride crystal. So when sodium chloride crystal is formed from the constant ion, that is sodium ions and chlorine ions, the amount of energy liberated or released is equal to minus 788 kilojoules per mole. So 1 mole of sodium chloride will liberate to form 1 mole of sodium chloride minus 788. Same way, if you want to break this, so you can do like this. So this implies that the formation of 1 mole of sodium chloride, 78 kilojoules of heat is liberated, as I told you. So for the formation and to break 1 mole of sodium chloride into its constituent ion, that is sodium ions and chlorine ions, the energy should be 788 kilojoules per mole. Means when you supply 788 kilojoules per mole for this sodium chloride, it will change to again back Na plus and Cl minus. I hope it is clear. Next. So what is this lattice energy? Why you are considering this lattice energy? Because it is related to stability of ionic compounds. Lattice energy of ionic compound is directly proportional to stability of ionic compound. So more the lattice energy. So this they'll ask in the competitive. This point they'll ask. So they'll give the lattice enthalpies of they will give the lattice enthalpy of different molecules, ionic compound molecules, and they ask which is more stable. This is one type of asking question. For example, they'll ask lattice enthalpy of sodium is this much of some energy they'll give. Lattice enthalpy of sodium chloride is, for example, sodium chloride, lattice enthalpy of sodium chloride, lattice enthalpy of magnesium oxide, like that they'll ask. So by using the lattice energy, what is that? Lattice enthalpy is directly proportional to stability of the ionic compound. So in between magnesium oxide, sodium compound, which is more stable depending on the lattice enthalpy. So with negative value, only have to take the value, not the negative sign. So during the formation of 1 mole of ionic compound, the system loses energy and a ionic compound gets stabilized. Higher the energy lost, here important here you see, higher the energy lost, higher will be the stability. Higher will be its stability. So this is nothing but lattice enthalpy. So how lattice enthalpy depending on the stability of the ionic compound based on lattice enthalpy depends upon high stability of the compound is nothing but directly proportional. So lattice enthalpy is directly proportional to stability of the compound, stability of the ionic compound. So more energy is lost, higher the energy lost, higher will be the stability. I hope it is clear. So this is the dependence of lattice energy on the stability of ionic compound. Next, lattice enthalpy and ionic, the lattice enthalpy or lattice energy. Lattice enthalpy or lattice energy of an ionic compound is due to strong attractive forces between the oppositely charged ions and also the repulsion forces between like charged ions. Like charge means, as I told you, in sodium chloride crystal, so many sodium chlorine ions are there. Sodium ions will be there. They are nothing but like charges. And so many chlorine ions are there. They are nothing but like charges. And cation, and anion. So like charges already repulsion takes place, and unlike charges attraction takes place. So the magnitude of lattice energy cannot be experimentally determined. However, the lattice energy is theoretically calculated using Born-Haber cycle. So this Born-Haber cycle, this we are going to do next topic. So what is energy? The lattice energy of an ionic compound is due to strong attractive forces between the oppositely charged ions and also the repulsion forces between the like charged ions. So oppositely charged and strong attractive forces as well as repulsion forces. So next. So how to calculate lattice energy? Q1 Q2 by R square. That is nothing but Coulomb's law. You know Coulomb's law in physics. So Q1 is called charge on one pair and Q2 is called charge on another pair. And R is the distance between them. So greater the magnitude of charge and smaller value of R gives a larger lattice energy. This lattice energy is nothing but, in other words, in physics we can say it is Coulomb's inverse square law, that is Coulomb's law of force of attraction. So Q1 Q2 by R square. I hope it is clear. Now example 1, we'll discuss now what is write the Lewis dot symbols for the following atoms and ions: sulfur and S2 minus. So sulfur, if you take into consideration, sulfur atomic number is 16. It has 6 valence electrons. So for everywhere, if you want to do all the chapters, the main chapter is periodic classification, which you have discussed in the last session. So periodic classification, if you learn properly, then only you can say. So the atomic number of sulfur is 16. So sulfur has 16 means it has how many electrons in the valence shell? So sulfur is 6 electrons in the valence shell. So you can write 6 electrons like this. 6 electrons, and S2 minus, it is gaining 2 electrons. So sulfur S2 minus, you can write like this: 1 2 3 4 5 6 7 8. So this is the diagram. So in this way you can write phosphorus as atomic number 15. So 15 means 5 electrons in the valence shell, and the P3 minus means 18. So 18 means 8 electrons in the valence shell. So you can represent them clearly like this. So example I already have showed you. Now we'll see the answer. So this is nothing but, so sulfur has 6 electrons in the valence shell, and phosphorus has 3 electrons. So P3 minus. Now I think it is clear now. Next. Next. So these are the two questions which you have got from this session. More about this session we'll discuss now. Continuation. So I'm moving to next slide, next PowerPoint. Yes. So it has come to next PowerPoint now. So what is this now? Ionic bond determination of lattice energy. How to determine lattice energy by using Born-Haber cycle. As I told you. So how to determine what is lattice energy? Already we know. It is the amount of energy released during the formation of 1 mole of ionic lattice from its constant gaseous ions. So already we have seen the lattice energy of sodium chloride formation is minus 788 kilojoules per mole. It is nothing but that much of energy. That is minus 788 kilojoules per mole of energy is released during the formation of sodium chloride. And now what is this Born-Haber cycle? Because this is very important. Because everyone knows that the ionic bond is formed due to nothing but here. So they'll think that what is Born-Haber cycle? We'll discuss now. From Born-Haber cycle, we'll be knowing step by step formation of ionic bond. This is exact formation of ionic bond, which is very, very important for all the competitive exams. So now we'll see what is Born-Haber cycle. What is Born-Haber cycle? It is nothing but the experimental data. Theoretical energy is calculated theoretically using Born-Haber cycle. Now we'll see what is Born-Haber cycle. The Born-Haber cycle is based on the principles of Hess law of constant summation. This Hess law of constant summation, basic idea I'll give you, but you will get this Hess law of constant summation. This topic you will be getting in thermodynamics. So which we are going to discuss in the coming classes. So this is nothing but Hess's law of constant heat summation. According to this law, the amount of the amount of heat liberated or observed during a chemical reaction will remain same whether the reaction takes place is carried out in one single step or in multiple steps. So more about this Hess law we'll discuss in the thermodynamics. But just you see this crystal lattice that is Born-Haber cycle is based on the principle of Hess law of constant summation. This principle is applied for calculation of lattice energy of an ionic compound. So Hess law is applicable for lattice energy of ionic compound. So how to calculate lattice energy of sodium chloride we'll discuss now in this class. So the Born-Haber cycle for the formation of sodium chloride is as follows. First, already we know sodium exists as solid in nature because sodium is a metal. All metals are solids at room temperature, and chlorine is gas. And finally, they form sodium chloride. Delta H is minus 80, where delta H is enthalpy of formation of sodium chloride. That is only 1 mole. But now we'll see what is happening here. Very, very important. That total reaction which we have discussed in the previous. So the total reaction is nothing but here. See here, the sodium chloride. The sodium chloride formation is taking place in several steps. Now we are going to discuss that several steps. What are the steps involved? The sodium metal is vaporized into gas atom. As I told you, sodium exists as solid at room temperature. So first we have to give some energy that is called the amount of energy required to change the solid into gas, that is called enthalpy of sublimation. Why? Because we can change a solid into gas only by the means of the process called sublimation. So that is called whatever the energy is used in that is called as enthalpy of sublimation. I'm underlining it, you also underline your classwork. So this all the steps are important. The sodium metal is vaporized into gaseous atoms. The amount of heat required to convert 1 mole of sodium atom, 1 mole of sodium metal into gaseous atoms is known as enthalpy of sublimation, and that is taken as plus 108. It is observed. So plus 108.7 kilojoules per mole, because enthalpy of sublimation means we have to give the energy. So as the energy is absorbed, we will say this positive sign. Similarly, next, from this sodium gas atom, already I told you what is ionization energy. The amount of energy required to remove an electron from the neutral isolated gaseous atom. So the ionization energy of sodium atoms into sodium ions in gaseous phase. The energy required for this process is called equal to ionization energy. What is ionization energy? The amount of energy required to remove the electron, outermost electron of a neutral gaseous atom. So from sodium gas atom, we are removing one electron and it is forming sodium gas ion. And that electron we have to write left hand side minus, and it is writing right hand side will say plus electron. And this is called formation of sodium ion. First sodium ion is formed, and that is called in that delta H ionization energy. This is also positive because it is amount of energy required given. So plus 495.8 kilojoules per mole. So I hope it is clear. First step is clear. Second step, first step is nothing but conversion of sodium atom, sodium gas atom, solid atom into sodium gas atom. then removal of electron from sodium gas atom. So that is formation of sodium ion. So that is first case it is enthalpy of sublimation. Second case it is called ionization energy of sodium. So how sodium ion is formed? It is formed in two simple steps. So it's not so easy. So simply we are writing what is formation of ionic chloride, ionic bond in the school level, but here in PU level or college level, we'll be writing like this. Next, third step, involved in bond hypercycle. So the above reaction have the following steps. Next, chlorine molecule. As you know, chlorine is diatomic molecule. Chlorine is what? Diatomic molecule. First, the chlorine molecules are dissociated to form gaseous chlorine atoms. So the amount of energy required to break that bond, because already you know Cl2 exists as molecule. Cl2 does not exist. Chlorine does not exist as atom. Cl, chlorine exists as molecule. So Cl2 molecule. So first we need to break the Cl2 molecule into Cl atoms. So Cl atoms. So to break that Cl molecule into Cl atom, we have to give some energy. So the amount of energy required here also required. Required means always plus. The amount of energy required in this process is equal to half the bond dissociation energy. So that process called as bond dissociation energy. What is bond dissociation energy? The energy required to break the bond between two atoms is called bond dissociation energy. The energy required to break the bond between two atoms is called bond dissociation energy of chlorine. So half Cl2 gives rise to Cl gases, and in this case delta H is nothing but delta H of dissociation enthalpy or dissociation energy. Enthalpy and energy are same, so it is equal to plus 124.4 kilojoules per mole. All of you note down these values, and how will you apply Hess law for this we'll discuss now. So as this is very important, so Born-Haber cycle, so delta Hd. So this is called, first we have, first step we have what? Again I'm recollecting. First step we have enthalpy of sublimation. Second step we have ionization energy. Third step we have bond dissociation energy. Now we'll see fourth step. So now the above reaction will have the following steps. Now here the chlorine atoms in gaseous state. Now since chlorine molecule is big, he's been changed into chlorine atom. So this chlorine gaseous atom, already you know chlorine is a gas at room temperature. So straight away we'll get chlorine gaseous atom. And this chlorine gas atom accepts an electron to get converted into gaseous chloride ions. So the amount of energy released in this process, as it is accepting electron, so whatever the amount of energy it is gained by accepting that electron, that should be released into the atmosphere. So that is nothing but electron gain enthalpy. So this is called the amount of energy released in this process known as electron gain enthalpy. As it is released, released means we have to take amount of energy is minus 348.8 kilojoules per mole. So this is the fourth step. So amount of energy released. So the sodium ions and chlorine ions combine to form sodium chloride crystal. So sodium ions, gaseous ions, and chlorine gas ions combines together to form sodium chloride crystal. And in this case, delta H is equal to U. This we are going to find out. And this amount of energy released during this process is known as lattice enthalpy. So the amount of energy released during the process, which process? That is the formation of sodium chloride molecule from sodium ions and chloride ions, is nothing but lattice energy. Now we are going to calculate lattice energy, and it is represented by delta U. And what is delta U? We are going to discuss now. So, but that is based on Hess law of constant heat of summation. Hess's law of constant heat summation. So according to Hess law of constant heat summation is equal to the sum of heat changes of above steps. So if you all add all the above steps, that is nothing but delta H of the formation of sodium chloride is equal to delta H of sublimation, delta H of, so delta H of sublimation. First one is called what? Delta H of sublimation. Second one is called ionization. The third one is called delta H of bond dissociation enthalpy. Fourth step, electron gain enthalpy. And fifth step, finally, energy release. So this U. So U is equal to, by this you can say delta H of minus delta H of IE1 plus delta HT plus EA1. So what is delta H? If it is already given, it is equal to 380 minus 380, because that for 1 mole of a compound, it is minus, the heat of formation is minus 380 minus 108.7 minus 495.8 plus 124.4 121.4. And what is electron affinity value? Minus 348.8. Just use this formula and you'll get approximately minus 757 kilojoules per mole. Actually it is 788 or it is 757. It's almost same. So just very, very important. So this is called ionization crystal lattice energy. Crystal lattice energy of sodium chloride formation. Very, very important. I hope it is clear. So in this way you will calculate. So in the examination, competitive examination, they give sublimation energy, ionization energy, and of any molecule, not only sodium chloride, and bond dissociation energy, electron affinity value, and finally this value they will not give. U is called what? Lattice enthalpy. And heat of formation, delta HF is called what? Delta HF, I'm writing here. What is delta H? Because it is new to you. Delta HF is called, this is called heat of formation. Heat of formation. This is called heat of formation. So heat of formation is called delta HF. So delta HF is called heat of formation, and so this is called calculation of lattice enthalpy. I hope it is clear. Easily you can understand it. There is nothing but heat of formation is called all the sum of all the steps involved in the process. Sum of all the steps involved in the process is called heat of formation. And last step we don't know. So that U is called crystal lattice enthalpy, and U is equal to delta HF. You send all this 4 to that side, it becomes minus. I hope it is clear now. Next. Hence, during the formation of 1 mole of sodium chloride, lattice enthalpy is calculated as 757.1 kilojoules of heat is liberated, as it is negative. The Born-Haber cycle can be represented as diagram. Diagram you can see here. First, solid sodium and chlorine gas minus 380 kilojoules per mole solid sodium chloride. This takes place in so many steps. First, solid sodium changes to sodium gas atom. From there, it changes to sodium gas ion. Chlorine molecule, half Cl2 we are taking, changes to chlorine gas atom, and bond dissociation enthalpy is 121.4 kilojoules per mole. And this chlorine gas ion and this sodium ion and chlorine gas ion combines to form crystal lattice enthalpy, and this U is called crystal lattice enthalpy. I hope this diagram is clear. Clear this diagram. Again, I'm showing the diagram. You can see this diagram is clear. I hope it is clear now. So this is called Born-Haber cycle. So in this way, like this, deeply we'll go into the concept. Just in 10th class level, what we have, they have given only formation of sodium chloride, but how it is formed totally we have been discussed now, that is using Born-Haber cycle. So that is the difference between 10th and 11th. I hope it is clear now. So from these objective questions, how they give, they calculate, ask us to calculate that is enthalpy of a given molecule, and they'll give all the process steps. And if always first, very very important point to have to remember, that important point I'm writing here. So a metal will not lose electron. A metal will not lose electron in solid state. Only it can lose electron in gaseous state only. Metal will not lose electron in solid state. It can lose electron only in gaseous state. So first we have to convert the metal into gaseous state. So we have to convert the solid sodium into solid gas, gaseous sodium. Very very important. So metal will lose electron only in gaseous form. Only in gaseous form it can lose electron by giving ionization enthalpy. Otherwise, from solid, we cannot directly get ionization enthalpy. If you give a solid for solid ionization enthalpy, it will not give electron. So whenever a metal lose electron, and in what position a metal will lose electron? Only in gaseous state. I hope it is clear now. So that point is most important. So they will give all the ionization enthalpies, electron gain enthalpies, whatever the process taking place in the formation of that molecule, and they ask us to find crystal lattice enthalpy. And then most importantly, they will give heat of formation of reaction. So this is called heat of formation of reaction. Minus 380 means you have to take it as plus 380 on the right hand side. So this is called heat of formation of the entire reaction. And from that heat of formation, you can find out lattice enthalpy. So heat of formation is equal to sum of all these energies, including lattice enthalpy. So U is equal to heat of formation minus all these enthalpies. I hope it is clear now. So very, very important Born-Haber cycle. Next. So Born-Haber cycle continued. Lattice energy, sum of the ionic compound is given below. Higher the lattice energy, this already we discussed. How can we say about stability of the ionic compound? Higher the lattice energy of the crystal, higher will be the stability of the ionic compound. This point already we have discussed in the previous slides. It can be observed that the lattice energy increases with the increase in charge of ions. These are the factors affecting lattice energy increases with the increase of charge of ions. Also, the lattice energy decreases as the size of either lattice energy decreases as the size of or both ion increases. For a given cation, the lattice energy decreases with the increase in size of an ion. The lattice energy decreases with the increase in size of an ion. These are the factors affecting lattice energy. All these four factors are important. The order of lattice energy of halides of sodium is given here. Sodium fluoride is having more lattice energy than sodium chloride, than sodium bromide, than sodium iodide. Because of these factors only. What is the first factor? Higher the lattice energy of the crystal, higher will be the stability of the compound. It can be observed that lattice energy increases with the increasing charge of the ions. Fluorine is more electronegative than chlorine. So as the charge is more in fluorine, so it has more electronegativity than sodium chloride. Similarly, also, the lattice energy decreases as the size of either or both ion increases. As the size of ion increases, lattice energy decreases. So you can see here, sodium ion is stable here, but iodine size is more. So increases or decreases. So the order of lattice. So with the increase of anion, so sodium iodide is having higher ionic size because of a higher atomic number. So as sodium iodide is less ionic than sodium fluoride because of small size of anion, and here large size of anion, small size of anion, large size of anion. So like this, the order goes like this. This order is important. They'll ask, are in the following the decreasing order of the lattice enthalpy, or in the following in the decreasing order of the stability of the compound. So which is more stable? Sodium fluoride is more stable than sodium iodide. The order of lattice energy of fluorides of different metals is given as lattice energy of sodium chlorides of different metals. Sodium chloride is less than MgCl2, less than AlCl3. So AlCl3 is having more lattice enthalpy. So sodium chloride is less than MgCl2, MgCl2 is less than because of size, charge. So if we take charge here +1, and here it is +2, and here it is +3. So the charge of aluminum is +3. So I hope it is clear. So this slide is very very important. You can just note it in your classwork. Very important this slide. Next. So the lattice energies of different compounds is given. Lithium fluoride 1030 kilojoules per mole. Lithium chloride means this much of energy is liberated during the formation of lithium fluoride crystal. Lithium chloride, this much of energy is liberated. Lithium iodide, sodium chloride, sodium bromide, cesium iodide, and MgCl2, SrCl2, MgO, CaO, and these are just experimental values. You can see here scandium nitride is having highest lattice enthalpy, means it is most stable compound. 7,547, and so you can see here this is important. Next now we'll see, before going to this, so this is scandium. So next we have properties of ionic compounds. All properties, very very important. The ionic compounds are crystalline in nature. The crystal lattice is found by the close packing of cations and anions. So ionic compounds are crystalline in nature. The crystal lattice is found by the close packing of cations and anions. These compounds possess, as they are solids at room temperature, ionic compounds, they possess high melting point. This point is important for objective. Then ask which of the following is true regarding ionic compounds. They possess high melting points and boiling points because most of the ionic compounds, almost all the 99.100% ionic compounds are solids at room temperature. So these compounds have high melting points and boiling points. And this is due to strong electrostatic force of attraction between them, between the oppositely charged ions. So these compounds are hard and brittle in nature. As they are solids at room temperature, they are hard. All the properties of solids will come into existence. The ionic compounds are usually soluble in polar solvents like water. So almost all ionic compounds are soluble in water and they get ionized in water. For example, when you dissolve sodium chloride in water, it forms Na plus and Cl minus. So the ionize in water. They ionize in water. So that's why they are soluble in polar solvents and they are insoluble in non-polar solvents. So all ionic compounds are soluble in polar solvents. I hope it is clear. Next. So all ionic compounds, these are good conductors of electricity in solution only. Very, very important here. They are, all these properties are important. So they could conduct electricity only in solution. In solid sodium chloride cannot conduct electricity. Only molten sodium chloride can conduct electricity. So here I'm writing here molten or in solution wise, molten NaCl conducts electricity, whereas solid sodium chloride does not conduct electricity. Does not conduct electricity. No electricity. So solid sodium chloride conducts electricity, but not solid sodium chloride do not conduct electricity. Do not conduct electricity means they are not good conductors. Only in molten state and solution same. So here I'm underlining solution, electricity in solution or in molten state. But they are poor conductors in solid state. These compounds show isomorphism. What is isomorphism? Different compounds can exist both with same crystalline structures. For example, NaCl and MgO are isomorphous to each other, means they have same crystalline structure. These ions have same electron configuration in both the compounds. Similarly, potassium chloride. Why same electron configuration? You can see sodium has 10 electrons in the valence shell and chlorine has 18 electrons. Similarly, oxygen 8 electrons in the valence shell. Similarly, magnesium and oxygen, they are isomorphous to each other. Isomorphous means with same crystalline structure. Simply, different compounds can exist with same crystalline structures. They are said to be isomorphous to each other. The ions have same electron configuration in both the compounds. Similarly, potassium sulfide and potassium chloride. So they'll ask an objective, which of the following are isomorphous? Isomorphous means having same crystalline structures. Very, very important. As they're having same crystalline structures, they are said to be isomorphous with each other. I hope it is clear. So isomorphous to each other. Next. So solubility and lattice energy of ionic compounds. Generally, ionic compounds are soluble in polar solvents like water. This already we discussed. The solubility of ionic compounds in water is due to hydration of ions. As I told you, in water they form ions in the solution. When ionic compound like NaCl is added to water, sodium ions are surrounded by water molecules in such a way that the oxygen end of the water molecule, the oxygen of the water molecule is towards the sodium ions, and chloride ions are surrounded by water molecules with hydrogen end towards. So hydrogen H plus ions of water molecules surround chloride ions. So in this way, that's why there is nothing but what due to hydration of ions in solution. That's why they are soluble in water, as I told you already. So they are soluble in water only due to hydration of ions. Means they ionize in water. All the ionic compounds ionize in water. That's why they are soluble in water. Next. This phenomenon is known as hydration, and the energy released during this hydration is known as hydration enthalpy or hydration energy. Since water is a polar solvent with high dielectric constant, because the dielectric constant of water is high, so the ions are separated and thus the compound dissolves. Thus, the ionic compound is soluble in water if the hydration energy of its ions is more than the lattice energy of the compound. Very, very important point. This point also they will ask in the objective. So, whether the compound is soluble or not. When the compound is soluble in water, if the hydration energy of its ions means the ionic compounds is more than the lattice energy. So if lattice energy is more than hydration energy, the compound is insoluble. If the lattice energy is less when compared to hydration energy, the compound is soluble. If the hydration energy of its ions is more than the lattice energy of the compound, it is soluble. Otherwise, if the lattice energy of the compound is more than the hydration energy of the ions, the compound is insoluble in water. So usually the covalent compounds will have this, will find this thing. If the lattice energy of the compound is more than the hydration energy of the ions, the ionic compound is insoluble in water. We can say certain insoluble salts. Insoluble salts will have lattice energy more when compared to hydration enthalpy. So due to which they are insoluble. So we have some ionic compounds. Most of the ionic compounds, as I told you, not all the ionic compounds. Most of the ionic compounds are soluble in water because their hydration energy is greater than the lattice energy. If the hydration energy is lesser than the lattice energy, or the lattice energy is greater than the hydration energy, the ionic compound is insoluble in water. I hope it is clear. This slide is very important for objective point of view because they'll ask about solubility. Solubility, whether compound is soluble or not, and why it is insoluble also. So I hope it is clear. Now I'm ending this class. I hope all the, today we completely ionic compounds. Completely ionic compounds. More about ionic compounds we'll discuss, but ionic compound is, to my knowledge, it is over. So I'm ending this class. I hope it is clear.